Hello, welcome to another video of sectoral structures theory. Today we will focus on some of the number theoretic aspects of this theory. We mentioned earlier that we will see many patterns related to number theory within the framework of sectoral structures theory, and this is mostly related to the Meem function. So let's begin. Today we will be focusing mostly on the Meem function. We will see some of its connections to well-known functions in number theory, but also we want to focus on its connection to prime numbers. So let's begin. What we're going to do is we will show the Meem function in its two primary forms, one for the even numbered values of n and one for the odd values of n. And that's really the most natural way to see it. In a way, the Meem function has two natures, one that applies to odd functions and one that applies to to odd values, and one that applies to even values. But for ease, we sometimes try to merge them into a single equation. Let's review the even function for n, for Meem. So we know that Meem of n is equal to 2 to the power of n minus 2 plus 2 to the power of n minus 2 over 2. Now, if you see it in this format, it's really simple. So that's why when we split it into its two forms, it becomes a lot simpler. When we try to merge them together, it becomes a little harder to see. We can factor this into this simpler form, which is 2 to the power of n minus 2 over 2 times 2 to the power of n minus 2 over 2 plus 1. We see that this is if we consider this to be x, this is of the form x times x plus 1. So we see there that it's really a nice way to look at it. Now this can be further simplified or expressed differently, not really simplified. We can express this because this is equal to x times x plus 1. We can express this as in terms of factorials. We can say that Meem of n for even values is equal to 2 to the n minus 2 over 2 plus 1 factorial over 2 to the n minus 2 over 2 minus 1 factorial. So really we expressed it as this form, x plus 1 factorial over x minus 1 factorial, which simplifies to x times x plus 1. Now for the odd values of n, Meem of n is equal to 2 to the n minus 2 plus 2 to the n minus 3 over 2. We can simplify this further into this form, 2 to the n minus 3 over 2 times 2 to the n minus 1 over 2 plus 1. Now this, if we want to consider this to be x, we can say that this is the equivalent of x plus 1 times x, and then we have a minus here, so that will become 1/2. So we can also express it this way. Now, if we want to express this as in terms of factorials, we will say this is equal to 1/2 times 2 to the n minus 1 over 2 plus 1 factorial over 2 to the n minus 1 over 2 minus 1 factorial. So really this is just saying x plus 1 factorial over x minus 1 factorial, and we are multiplying it by half. So this really helps us to see that this function here, um, whenever we want to see the values of meem of n, sometimes if you look at the trend, if we look at some of the values 1, 2, 3, 6, for example, whenever we go from an odd value to an even value, we multiply by 2. Or here we multiply by 2. But when we go from an even value to an odd value of n, we do something else. So we don't multiply by 2. But this is why we see there is this factorial pattern here and half of it when it's odd. Now, once we express it in factorial form, we can do a few more things. We can see its connection to the gamma function and the beta function. Those are the functions from number theory. So what we're going to say is the following. We're going to try to express both of these as a single equation again, but this time we're going to use the mod format. So let y equal n mod 2 plus 1. So if n is equal to 3, we will say 3 mod 2, that's 1, plus 1 equals 2. So y will be equal to 2. And let x be 2 to the power of n plus y minus 3. Now, if we use this expression, we can simplify meem of n for both of the values to the format x plus 1 factorial, where this is x, as we've seen, but here we are defining x a little differently, over x minus 1 factorial, and then we are dividing this expression by y, which is right here. Now, there are other ways to express it if we're going to use this format, but this is the one we're going to use here. Now, going from this format of meem of n, we can express this as a gamma function very easily. We can say meem of n is equal to gamma of x plus 2 over y times gamma of x. So here we found a way to express meem of n in terms of a gamma function. And remember, at any point, we can substitute x and y and end up with a single variable equation. Now, going from this, we can further express it as a beta function, which is even simpler. So meem of n would be equal to 1 over y times beta of x comma 2. Now, this was just really to show us some of these connections, but what I really want to focus on is the connection to prime numbers, because that is a very profound connection. So we have here the values of n, and then we can here imagine that we're going to list all the different values of meem. So it will be something like this, 2, 3, and so on. And then here we have meem of n mod n. So what is meem of n mod n? Let's do an example. Let's say we have for the value of n is equal to 4. We know that meem of n would be equal to 6 because the size of that sectoral set is 6. And then we would say meem of n mod n, that would be 6 mod 4, and that would be equivalent to 2. Okay? So this is what it means. So there is no reason, as we see here, we got 2 there's no reason why we should get a specific number. And in fact, when we do this, we get numbers that are very different. However, something very interesting happens when the value of n is a prime number. Not an odd number, just a prime number. So if n is a prime number, and we have the different values of n here, so 2, 3, 5, 7, 11, and so on for the prime numbers, we calculate meem of n for each of them, and then we find meem of n mod n. And a very remarkable pattern emerges. For all the odd values of n, meem of n mod n is always, and you can do this for a very large number of n values. And now we will also show an algebraic proof. N, or the result, will always be either 0 most of the time or 1. And this is very remarkable when you look at it from a distance. So whenever you have a prime number, meaning whenever you have a sectoral set where the structures have a degree that is a prime number, then the size of that sectoral set mod the degree of the structures will always be either 0 or 1. And the choice whether it's 0 or 1 is also not arbitrary, as we will shortly see. So this is pretty significant when you think about it. But now then we see that this is deeply connected to Fermat's little theorem. So here we see a connection, very clear connection with number theory. So if we remember, or if we use the prior expression, let's forget the value when n is equal to 2 for now, even though it applies to it. And let's focus on the odd primes, which are all the primes except 2. Then we're gonna look at the odd or the odd formula for meem of n. So meem of p, when p is odd, is equal to 2 to the p minus 2 plus 2 to the p minus 3 over 2. Now this can be expressed as, or 2 to the p minus 2 can be expressed as 1/2, and you'll see why we're going to express it this way. 1/2 of 2 to the p minus 1 over 2 squared. So again, 1/2 of 2 to the p minus 1 over 2 squared, plus we're going to express this other side here as 1/2 2 to the n to the p minus 1 over 2 to the p minus 1 over 2. So notice we have 2 to the p minus 1 over 2 on both of these, on both sides. So if I'm going to use x to express 2 to the p minus 1 over 2, this would be 1/2 x squared plus x. So 1/2 x squared plus x. Now, we know from Fermat's little theorem that 2 to the p minus 1, or 2 to the power of p minus 1, is congruent to 1 when a mod p, when p is a prime number. And here it should become very clear now why there is such a connection, because meem of n is really um, a, a power of 2, a sum of 2 powers of 2. And Fermat's little theorem is also related to powers of 2. And we are focusing on the values that are prime. So what does this mean? This means that 2 to the power of p minus 1 over 2 squared is congruent to 1 mod p. Because this is really, if you multiply by 2, you get the same thing you have here, which is 2 to the p minus 1. So we just expressed it differently. We divided it by 2, and then we raised the whole expression, we made it squared. So by simple exponent algebra, we can go back to 2 to the p minus 1. So therefore, we can say that this whole first expression here is really equal to 1/2, or not equal to, but congruent to 1/2 times 1. Okay? Because this first part here, when it's prime, is congruent to 1. Now, what about the second part? Second part is 2 to the power of p minus 1 over 2. And we can see that this will be, when p is prime, this, we can use quadratic residues to solve this. And we will find the following rule. When we have, by using Euler's criterion, we know that a to the power of p minus 1 over 2 is congruent to either 1 or -1 mod p. So this is also established in number theory. A to the p minus 1 over 2 is congruent to either 1 or -1 mod p, where p is a prime number. So what does this mean? This means that the second expression is congruent to either 1 or -1. So notice what we have now. And you'll see this pattern is recurring in multiple ways in sectoral structures theory and in ways that don't seem related. So we have 1/2 times 1 plus -1 is always going to be equal to Meem of noon mod n. So that is 1/2 of 0 is 0, 1/2 of 2 is 1. So this is why we always get the result either as 0 or 1, and it's not a coincidence. It's always going to be this way when n is a prime number. Now let's take this another step further. Can we determine when it will be 0 and when it will be 1? Yes, we can. Because again, we're going to use quadratic residues. We will find that whenever we have the result as 1, then the number here, n, or the degree here, will be a quadratic residue for this expression. So let's see an example. So we know just experimentally that for 7 and for 17, we get a value of 1 instead of 0. So let's see what we have here. Let's look at 7. So let's say n, let's find another one. Let's say n is equal to 7. Then meem of n is equal to 36. And we can calculate this later. And then we want to find meem of 7 mod 7, which is the same as 36 mod 7, which is congruent to 1. Notice 36 here is a square number. It is 6 squared. So whenever meem of n is a square number, you will get a value of 1. So this is really nice that it's fine. These numbers are sorting themselves out this way. So you're connecting specific prime numbers with their quadratic residues. So I don't know Meem of 17. I haven't calculated it, but I'm pretty sure that it will also be a square number because we have a residue of 1. So therefore, we end up with this list of zeros and ones. And if we look at only the ones, we find a unique set of prime numbers. We will call these the Meem primes. So Meem primes. So what are the Meem primes? Those are the numbers or the values of n for which Meem of n mod n is equal to 1. Okay, so we will call these the Meem primes, and we can find the first few. They are 7, 17, 23, 41, 47, 71. And this is an established sequence that you can find online. It is a documented sequence. But this is a very nice application of this sequence. Throughout this mathematical framework, we will refer to these as the Meem primes. So these are the certain degrees where you get 1 for this result. Now, these Meem primes also have interesting incidences in certain parts of physics. I was trying to find some of these, and it was very interesting. So when we look at finite quantum systems, we can have a pretty nice application for this. When we also look at, like in number theory, the splitting of fields, we can also have a nice application of this. But basically, going back to finite quantum systems, it answers the question of which prime-sized quantum systems admit a coherent quadratic symmetry. So I can't go deeper into quantum physics because I don't have a very deep understanding of the quantum physics. But this is the second time we've seen so far that these numbers that are emerging from sectoral structure theory have some application within quantum physics. And this is going to keep recurring. As we go forward, you'll see even more applications within organic molecules. And even more interestingly, you will see them with large biomolecules such as RNA. And this really goes to show that what we are looking at here is a unique way of counting and a unique way of understanding additive number theory that is intersecting with various types of natural sciences as well. Why? I think because it's a very natural way of counting things. We're bringing a circle, we're dividing it into equal sectors, and we're just twisting and untwisting the joints to generate all of these different numbers.